Good day everyone. Today for paper study assignment, I'll be studying system dynamics modeling approach to quantify change orders impact on labor productivity, principles and model development comparative study from the author of Zain Ghazi, Al-Kofahi et al. From University of Central Florida, Orlando. In construction projects, change orders are a common occurrences. This order, often issued by project owners, can disrupt the contractor's workflow, leading to productivity loss, delays, and cost overruns. The objective of this study is to develop a system dynamics model to quantify the impact of these change orders on labor productivity and provide insight for better project management practices. Labor productivity is a critical metric in the construction industry and is defined as the working hours required to accomplish a given unit of work. It directly affects the project timelines and costs. Change orders can have both positive and negative impacts on a project. The study employs system dynamics modeling using fancy software to investigate the impact of change orders on labor productivity, quantifying productivity loss, and linking this loss to causes. Key variables, both endogenous and exogenous, were identified to build the model by studying the literature. The methodology involves several steps: building the model, specifying inputs, running the model, examining the outputs, and finally interpretation and analysis. After determining the parameters used in the modeling, the CLD is constructed to understand the system structure better, based on cause-effect relationship among parameters. The causal or feedback loops are determined to outline the relationship among system variables, which are not necessarily linear but circular chain of cause and effect, as shown here. We can see 3 balancing loops and 2 reinforcing loops. An SD model, the stock flow diagram, was developed based on highly established and validated models in the previous studies. When the contractor wins the bid, he or she must do certain amount of work as specified in the bid document's work to do. During the simulation, this amount of workflow will through work being done toward the work done stockpile at the prescribed work rate, depending on the contractor's best productivity. When the project owner issues change orders, they add work items to project scope. It is hypothesized that the productivity can be impacted. Factors such as scope change, temperature, labor crowding, overtime, fatigue, and learning effect create feedback loops that affect the contractor's productivity as well as the workflow rate. This model studies the impact of different factors on productivity, labor hours needed to finish and deliver project on time, and the rate of work done. To validate the model, 2 highway construction projects from the Florida Department of Transportation were used as case studies. Data was collected from daily work reports, contract documents, and inspection reports. The model was then applied to this real-world scenario to test its accuracy. The processes by which model validation is accomplished include model conceptualization that follows by implementation of policy recommendation. SD model has specific characteristics that make standard statistical tests inappropriate. Different tests were suggested to evaluate SD behavior quantitatively, and such tests focus on measured time patterns rather than individual data points, including reference mode and statistical behavioral mode. Here, the historical fit is evaluated. As indicated here, the result of the simulation includes all the effects, relatively accurate, reproduce the project data regarding the work really done. The model was rerun without including the effect of the learning curve. Results are shown here. It must be noted that both runs are compared to the actual project outputs. Fancy model behavior is assessed using statistical model validation, which implies how successful the model will be when applied to the new data. Different statistical validation techniques have been designed using a comparison of the values predicted from fancy model and an independent validated statistical model. A model was built for the actual work done within the project period. Since the available data was limited, it was impossible to collect new data. The original data was split into two parts. First part was used to build the statistical model and estimate its parameters. The second part was used to assess the fitted model predictive ability and to run the model, tabulate the estimated value, and compare them to their counterparts from the fancy model. The coefficient is determined as a value of 99.8%, implying the model equation relating work really done to the week can explain that 99.8% of the variation percent present in data values of work really done. The plotted cumulative man-hours graph along with the residual plot can be seen here on the right side. The statistical model predicted data closely resembling the SD model data, and thus our model has been statistically validated. The model was validated through several steps, including verification and comparison with actual project data. The results showed a high correlation between the model's prediction and the actual outcomes. Key findings indicate that change orders significantly impact labor productivity, primarily through increased fatigue and labor crowding. In conclusion, the system dynamics model developed in the study provides a robust tool for quantifying the impact of change orders on labor productivity. It helps contractors and project managers make informed decisions to mitigate productivity loss. Future research should focus on exploring more variables such as weather condition, labor skill level, and technological advancement, and quantifying the positive impacts of change orders. Thank you for your attention. This concludes the presentation, and I would like to open the floor for any questions you may have. Feel free to ask about any aspect of the study or the model by writing in the comment section. Thank you. Have a good day.